This is Chapter 14, Section 1. In this chapter, we're going to be talking about acids and bases, and we'll go over several ways to classify acids and bases. We'll cover one of those ways in today's lesson. So first off, our acids. I have 5 different properties of acids. You need to make sure you get all 5 of these written down. The first one is acids have a sour taste. They do change the color of acid-base indicators, and there are multiple acid-base indicators that we could use, so it's just going to depend on the indicator itself. The third one, some acids react with active metals and release hydrogen gas. If you remember back when you were doing types of reactions, in this one, this is a single replacement reaction. And we have what I call a free element. I'm going to do some underlining as we go. The free element in this case is barium, wants to replace something in sulfuric acid. The free element has to be more active than what it replaces. So if you ever remember talking about the activity series, you can look up an activity series. If you're in class, you can look on page 278 and get a copy of the activity series. But in the activity series, your free element needs to be more active than what it's going to replace. And in this case, since barium typically takes on a positive charge, if it's an ion, it wants to replace whatever is the positive charge in the compound. So in sulfuric acid, hydrogen has that positive charge, and barium is more active than hydrogen. You'll notice that your group 1 and 2 metals tend to be fairly active. It'll kick hydrogen out. That's producing hydrogen gas, and you can see you have hydrogen. So now barium and sulfite get together to form a compound, and over here, if they have like charges, +2, -2, which cancel, so you get barium sulfate. And that is our solid. Hydrogen gas is released. So some acids will react, so your active metals will react with acids and release hydrogen gas. The fourth property, your acids react with bases to produce salts and water. So if you have an acid-base reaction, you get a salt, and water is also formed. An example of this, if we had hydrochloric acid react with sodium hydroxide, and you'll learn all about different acids and bases. This is a strong acid and a strong base. Then basically through a double replacement reaction, sodium chloride, which is your traditional table salt that you know of, but salts are any metal with a halogen, and water are produced. And then the fifth property, acids do conduct electric current. It depends on if it's a strong acid or not, but they can conduct electricity. So make sure you get these 5 properties. Looking at acid nomenclature. So how do you name acids or come up with their formulas? This slide is going to concentrate on binary acids, so that is hydrogen plus 1 more element. So you can see in the 4 examples that they give, you've got hydrogen plus 1 more element for binary acid. And for their nomenclature, the name of the binary acid begins with the prefix hydro and ends with the suffix ic. And you take the root of the elements, so the fluor for fluorine, the chlor for chlorine, the brom for bromine. You get the idea. And that goes in the middle. So hydro, put in your root element in the middle, and then the ending is ic. This is going to be for binary acids. And I will summarize this after we look at oxyacids. Here's several different formulas, and you can see their acid names. Again, all of these are hydrogen plus 1 more element, and they are hydro something ic acid, and you can see those particular names. Notice the formulas on these too. The number of hydrogens depends on the charge of the anion that it's with. So fluorine is a negative charge, chlorine negative, so is bromine iodine because they're all in group 17. The sulfide ion is a 2-. So as I'm looking at it, To combat those charges, you need one hydrogen to go with the fluorine, because that's typically a positive charge. Hydrogen is, unless it's with a metal, but you will need two hydrogens to combat the sulfur as far as its charge to get you a neutral compound. That's why you see H2S. So we've looked at binary acids and now oxyacids. So oxyacids are still going to have hydrogen as part of those since they are an acid, so you still see your hydrogen. But they will also contain oxygen plus a third element, which is usually a nonmetal. And there is a pattern that it follows, and the names of their anions are based on the names of the acids. So I'm going to add a slide right here, and we're going to look at the binary and oxyacids, just a quick way to look at these. So our anions, if you're looking at your pink sheet that you have or a list of ions, polyatomic ions typically end in ate or ite, and I will even denote that these are typically polyatomic ions. Putting them in parentheses, probably still a good idea for you. And the rest of our anions typically are going to end in ide, IDE. So your fluoride, chloride, bromide, things like that. The acids. So if you are trying to take, for instance, the sulfate ion and make the acid, typically you just drop off the 8 and you put ic. But instead of sulfic acid, it's sulfuric acid. We do have a couple that are that way. Instead of so for your phosphate ion, instead of phosphic acid, it'd be phosphoric. So we add a couple more letters. But your 8s are replaced with ic for the acid name. If the anion ends in ite, such as nitrite, then the acid name ends in OUS, so the nitrite ion would be nitrous acid. And like I said earlier, the number of hydrogens that you need, because hydrogen will have its typical positive charge in an acid, will depend on the anion's charge. So if you have a 3- charge on your anion, you will need 3 hydrogens, and hydrogen is typically at the beginning of the formula. Now for that last part, the ide, the majority of these are going to be based off of having only 2 elements, so hydrogen plus 1 more. So for our binary acids here, so your monatomic anions, the ending is ic also, but this time we add a prefix, which is hydro, and we did look at that when we were looking at binary acids. So for your acid names, the only one that gets an additional prefix is hydro. If your polyatomic ions have a prefix as part of their polyatomic ion name, those stay where they're at, such as perchlorate would be perchloric acid, or hypochlorite would be hypochlorous acid, so that per and that hypo are part of the polyatomic ion name. So here's several more examples of acids. Again, it's giving you the anion name. So if they end in ate, you can see the 8s have been changed to ic. If they end in ite, so I see some ites right down here, the ites have been changed to OUS. OUS. And this, we're going to give some common industrial uses for some acids. Please make sure you get these written down in your notes. Sulfuric acid, most commonly used, it is the most common acid used in the chemical industry within the world. It's also in your car batteries. You have nitric acid, which is common. Phosphoric acid is common. You'll find that in some of your drinks. Hydrochloric acid is concentrated solutions of it are known as muriatic acid. You have hydrochloric acid in your stomach. And then acetic acid, y'all are very familiar with this. Acetic acid is also known as glacial acetic acid, but if you have a typical or a common 5% mixture of acetic acid with water, then you have vinegar. And I know all of you are familiar with vinegar. Now, that is some of our common properties of acids. Now let's look at bases. We have some properties here. For your bases, they typically taste bitter. So your acids tasted sour, these are going to taste bitter. Not saying you should try all of them, but some of our foods have that in there. Bases also change color in an acid-base indicator. If we're going with a traditional acid-based indicator, acids turn red, bases turn blue. They do feel slippery if you're thinking about lye soap, and then they will react with acids to produce salt and water. That was under the previous one. I gave you an example of this one, the hydrochloric acid, sodium hydroxide, producing sodium chloride and water, and they will also conduct electricity. The majority of our bases are ionic compounds. So we're going to get to the first classification of how you could classify acids and bases, and this is Arrhenius. So an Arrhenius acid is a compound that increases the concentration of hydrogen ions. So increases the concentration of hydrogen ions, and an Arrhenius base increases the concentration of hydroxide ions in solution. When it's talking aqueous solution here, they're talking about the hydrogen ion. Aqueous means it's dissolved in water, and that would give you the hydronium ion. So if I were just abbreviating this right here, because again, we have a few different classifications we'll get to within the chapter. An Arrhenius acid increases hydrogen ion production, and an Arrhenius base increases hydroxide ion production. I'll try to underline the important parts here. Arrhenius acids are going to be compounds that have ionizable hydrogen atoms. Their water solutions are known as aqueous acids. We just looked at that, and all aqueous acids are electrolytes. So all aqueous acids are electrolytes. The example they give here, we have nitric acid that is being dissolved in water to produce the hydronium ion and the nitrate ion. So again, your hydrogen ion concentration is increasing. Please make sure you write down this chart. Write down this chart, and I will explain parts of this. So we have a difference between strong acids and weak acids. We've already briefly mentioned electrolytes, strong electrolyte, weak electrolytes. So our strong acids will be strong electrolytes. Weak acids will be weak electrolytes. I have 6 listed here. You can also add nitric acid to this list as being a strong acid. So hydroiodic, perchloric, hydrobromic, hydrochloric, sulfuric, chloric, and nitric acid. All of these are considered to be strong acids, and it's showing you the reaction with water to break into the hydronium ion, again, hydrogen ion, and the other anion that is associated with it, whether it is monatomic or polyatomic. And then your weak acids, again, you're producing the hydronium ion, but you can see some of your weak acids. The most common weak acids we'll probably see or talk about hydrofluoric and acetic acid will be the 2 most common ones. But I would get all of these within your notes. So getting back to the strength of these acids, a strong acid will completely ionize in solution, and it is a strong electrolyte, so it does conduct electricity well. And then your weak acids will only release a few of these hydrogen ions in solution, so we say that they usually break down about 3 to 5% of the acid will actually ionize. And then again, in a strong acid, that's basically 100% of it will ionize. So you have a few more examples right here. And then getting over to our bases, like I told you earlier, most bases are ionic compounds, so they're going to contain a metal with a hydroxide ion. Ammonia, though, a little different. It is a molecular compound, but it does produce hydroxide ions when it reacts with water. So this reaction, again, because ammonia is pretty common to talk about, make sure you get that reaction down because it is a little different than the typical metal with hydroxide that we're looking at up here. So there is an example there. So the strength of these is pretty much the same way. The strength of the base does depend on how much the base dissociates. So again, we use the word dissociate for ionic compounds. Your strong bases are going to be strong electrolytes because they will completely break down, 100% dissociate within solution. And then your weak bases, the ammonia is going to be the most common weak base we talk about, and you've looked at that. It will dissociate about 5%. I'm not going to spend a whole lot of time on this particular one right here because we will, in Chapter 15, completely break down the molarity based on pH of your different substances, if they're acidic or basic. But you can have those numbers in your notes. They'll make a lot more sense, though, in Chapter 15.